All right, you didn't hear anything that I just said, did you? All right, so let me go back and start over. Sorry, I was muted. I was talking to my wife. Okay, so I will start over. You should have sound now. Okay, so the plan for today is for those, most of you have not completed Lab 7, so I'm going to be as efficient as possible and going through Lab 7. Before I do that, though, I'll talk about the small changes I've made to the setup of my materials. So you couldn't hear me, but the reason why you're seeing my finger over here is because this is my little overhead camera. It's not the best. And the way I have it set up right now, it's upside down, so I'll have to figure out how I can position my camera to not have that be the case. But anyway, I have made some changes to the materials a little bit to try to help you since I talked to you yesterday morning. So I'll show you those changes really quickly. Then we'll go through Lab 7 and hopefully be efficient about that. Then we'll start in on the new content for this week, which is the two's complement part of the video title. And then we'll see how far we get. I'll at least try to get you started on Lab 8. So I've been drinking coffee, which means at some point we may need to take a short break. Since about 6 this morning. So we'll push as far as we need to without making everyone just disgusted with the experience, I hope. So anyway, let's get started. First thing I will do is I will try to get my browser back where you can see it. Give me a moment to position this. Okay, so let me just show you really quickly what I've done in terms of updating the materials. So one thing you'll notice, hopefully you're seeing that. Yeah, okay, I've got it. So I've added diagrams for all of the remaining projects instead of pictures. So I found a really cool piece of software called Fritzing, and I made diagrams. So for every project, there's now a simplified circuit diagram. So I'm looking at Lab 7, the simplified circuit diagram. Can you see the whole thing? You can. Maybe you can't quite see the whole thing. Let me shrink it. Okay, so I've made simplified circuit diagrams that show you just the breadboard part, and then you'll notice this thing is just making me crazy. You'll notice at the bottom I've put little labels to where these wires go on the board. So I don't have a picture of the Nucleo board, but I do have labels showing you where those wires go. So I'm going to wire up that circuit and go straight into Lab 7 this morning, barring any questions. So the first thing I'll do is just open up the floor for questions if there are any. Okay, so what you should be seeing here in a moment is my the vertical camera. So I'm going to take the board off. Don't need that right now. I've got pretty much a brand new kit for the circuit board. So I've got the breadboard, and that's as close as I can get the camera right now. So sorry about that. And I know the lighting isn't ideal, but I experimented with supplementing the lighting, and I just got more glare. So hopefully with the circuit diagram right there, you can work this out. So the main thing I want to show you about wiring these circuits up, which every semester people get confused about, when you open up you have this box, and you open it up and you have a whole bunch of resistors in there. That's interesting. On the camera, they look like they're tan colored, but in real life, they're blue. So I have to adjust the colors of the camera. But anyway, what's important about those resistors is to make sure that you get the right value resistor. So if you look at the diagram below, you'll see resistors are 220 ohm. So in my kit, I want to make sure that I get, let's see if I can get that where it shows in the camera. I'm shading it, I know. I'll get better at this, I promise. Anyway, one of these, the tape has 220 printed on it. So you want to use only the 220 resistors for LEDs. What I do once I start pulling them out of these strips is I keep them in a separate baggie, because these are the ones that we use the most often, is the 220 ohm resistors. So I'm going to grab myself for this circuit 4 of these. And I just pull them out. So I just grab them, pull them out. So I got 4 of those. They're all 220 ohm resistors. So now my strip has a gap on the end of it where I pulled 4 of them out. All right, so I'll set the resistors aside. I need 4 LEDs. I want 2-legged LEDs. Doesn't really matter what color. I just picked red and blue because I thought that for this circuit, it reminds me of the cops. So that's why I did that. And I don't know if it's true, but I heard that someone got followed to work by the cops in California, in Oroville, which I guess the cops were making sure they were on legitimate business. You know, police state and all. We're a little bit freer here in Arizona as of yet. So I'm getting 2 red ones. The important thing here is that they're 2-legged. So the 2 legs, and remember the long leg is positive and the short leg is negative. So I'm getting 2 red ones with 2 legs, and I'm getting 2 blue ones. Doesn't really matter the colors as long as you get 4 2-legged LEDs. All right, so now I can set the LEDs aside. I also need some wire. On the diagram, I used the same color wire everywhere, but it doesn't really matter. So it messes with my sense of order to not have sort of consistent colors, but the wires don't matter. The only thing that's important right now with the wires is that you get the male-to-male wires. So that's a male-to-male wire. So that's what you want, is male-to-male wire. I'm looking to see who I haven't welcomed in. So I think I already said hello to Anarchos. Good morning, Blaze, Brooksy. TMD, I don't know how to say that. V&K, Virgo, Praz. Good morning, everybody. Anyway, so I need 9 of these. I need 9 wires. You may have to experiment with the links to get the right links. But in theory, I need 5 longer ones. But if you get sort of this middle length wire, that's probably good. You can also do some short wires. So you can just experiment. All right, so here's my plan. I'm going to start by plugging in the LEDs. So notice one of them's long and one of them's short. So the way I do this is I bend the long one, kind of like sticking your knee out. And the reason I do that is because it's easier if they're kind of the same length here to plug into the board. And then the other thing I do is I just try to put every LED, I try to remember and put the long leg on the same side. It doesn't matter which side, I just put it on the same side so that I always know, oh, the positive is on the right, and the negative is on the left, or the positive is on the left. Just Makes life easier if you do it the same way everywhere. So I'm gonna, for you, I may have to try to do this upside down. I'm gonna try to do it upside down for you. So I'm gonna start up here. Try to match the board. So for me, let's see, what are you seeing? See where the long leg is there? So that's my left, your right. So I'm going to stick the long leg in. I've got 2 spaces in between them. It doesn't really matter. It doesn't have to have any spaces, but leaving a couple of row of spaces just makes life easier. So, and then I'm going to rinse and repeat. I'm going to switch colors. So I'm going to go red, blue, red, blue, red, blue. So I'll take this one. Bend the knee on the long leg just so they're kind of the same length, which makes it easier to plug into the board. And then long leg on the right, 2 spaces in between them. That one fought me a little bit, so I had to kind of wiggle on it to get it to go in. I am, just to make life a little easier, I'm kind of using, see that? So I'm kind of lining up the LEDs next to those. There's no real reason to do that other than it spaces them out nice so that when I take a picture of it for you, you can see what's going on. All right, I'm going to have to silence somebody here. Well, as long as they're not doing anything too bothersome, I'm not going to worry about it. Okay, so I'm alternating colors again. So same thing. I'm going to bend its knee for the 3rd LED. And then going to move over to the next section. And that's just to get consistent spacing and make it look pretty on camera. This one's also fighting me a little. All right, it gave. Oh, I forgot to switch colors. All right, so, and then the last one, I'll just move over to the next bank. And that's just to get consistent spacing again. It doesn't really matter. This one was already bent at the knee. All right, so that's step 1. I'll set my wires down. Okay, so step 2. There's no particular order, by the way. I picked this order. Step 2, I'm going to take the resistors. And the way I do the resistors is kind of bend them into a U. And again, just because I find it easier if the legs are kind of the same length, so when I press it into the board, it's kind of even. All right, so for this one, I'm going to take the resistor and I'm going to connect it on the LED side to where the long leg is. So this row right here. See if I can bring it up. So this row right here has the long leg on it. So I'm going to connect one leg of the resistor to that row where the long leg is. And then I'm going to bridge the channel. These fight me a little bit more. Like this board is fighting me a lot this morning. Okay, so what I have then is positive long leg, and on that same row is one connection of the resistor, and then I bridge the gap, and then I just picked a row and stuck the resistor in on that side. So I'm about to repeat that same process 4 times, well, 3 more times. So I'm going to get another resistor, I'm going to bend it into a U. if you really mangle a resistor's wires, just get a new one. Don't throw it out, but get a new one and just see if that helps. So I'm going to go to the next LED over. And connect to the long leg on this side. I'll show it to you when it's connected. And then bridge the gap. And that one's also fighting me. I think I've got it. We'll find out when we try to power it. Okay, so now I've got 2. So long leg, resistor, bridge the gap to other side, long leg. On the second one, resistor, bridge the gap. All right, 2 more. This breadboard is being particularly difficult, by the way. Okay, I think that one's probably in there. Hopefully it's in there. And then the fourth one. All right, that fought me every step of the way. Okay, so there's my 4 LEDs, 4 resistors. All the resistors are 220 ohm, remember. Okay, next step. Need some wires for this step. So I'm actually going to get, if I can find them, I'm going to try to get 4 shorter wires. The colors don't matter, but I'm going to get 4 slightly shorter wires, 1 for each light. If I could get 4 blue ones, I'd be thrilled. But well, there's 3 blue ones. Pretty close. The colors don't matter unless you're like me and it pleases you that they're all the same color. Okay, so I'll hit pause for a second, and in fact, while you're wiggling wires, I'm going to get a USB cable real quick. So give me a moment. I hope I have a USB cable. Okay. Don't need it quite yet, but I didn't want to interrupt myself when I got to that stage. Don't be shy if you want me to hit pause for a second. Otherwise, I'm going to move on to the wires. And maybe all of you have already done this. So, okay, so now I've got the LEDs connected. You can probably see, you might be able to see that I have the long legs in your view all on the right. And then I have a resistor connecting the long leg and then bridging the channel to a row on the other side. All right, so now what I'm going to do is I'm going to connect the short leg of each LED to ground, at least ground on the board. So get it where you can see it. Anyway, so I'm going to connect a wire, and I know you get sort of crammed in here. So this wire is on the same row as the short leg of this LED. And then I'm going to take that wire and connect it just anywhere. That one, I couldn't plug it in there. Okay, I moved it over one. So anyway, I'm basically bridging the short leg of the LED all the way across to the ground strip. And I'm going to do that for all 4 LEDs. So go to this next one. Same row as the short leg on this side. So the two are, so those 2 wires, that's on the short leg of this LED. This one's on the short leg of this LED. And then I'm going to bridge that to the ground strip. The colors, I may have to fix the colors in the camera, but anyway, that's negative, even though from what I'm seeing it looks red. Anyway, that's the negative, so these are both negative. Get all 4 wires like that. If I can. This board, by the way, I'm having to try different holes over here because some of them I just can't press the wire into without feeling like I'm really having to mush things. And then I'll plug this one in, maybe. Okay, so that's the LED wiring. And if you notice on the circuit diagram down there, I've done all of the stuff on the right except for the long wires that are coming out. So I'm going to worry about those next. So I need 5 wires. That's all the wires that are going out with little labels on them. I need 5 wires, and it's helpful to have longer ones for this part. So I'm going to get myself 5 longer wires. The colors don't matter. Unless you're like me and they do matter a little bit just because it would bother you. Although I don't have 4 or 5 of any one color, so I'm just doing my best. Yeah, my colors are all over the place. 1, 2, 3, 4, right? 1, 2, 3, 4, 5. Okay, there's 5 wires. So what I'm going to do with these wires is what's on the bottom of this diagram down here. So one of the wires simply comes off of the ground strip. And that's the one on the diagram that says 2 GND to ground. So I have that one. And then for each of the resistors, so this resistor right here, let me see if I get it in the camera better. So you have the long leg of the LED, you have a resistor on the same row. It bridges the channel to a row on the other side. So in that same row where the resistor is on the other side, I'm going to connect a wire. This one. So this wire right here is on the same row as the resistor right here. And that resistor bridges the gap to this row, which is the same row that the long leg of that LED is on. And then I'm going to do the others like that. So find the row where each of the resistors comes out. And I know it's getting hard to see on camera, but the row where the resistor has bridged the gap, and I'm going to connect a wire, if I can, yep, for each of those. I got one more, this one right here. So you may be having the same experience as me. So anyway, I have 5 wires. Those are the ones that connect to the Nucleo board. Now I'll just do what the diagram says. So, got my board. So we can go in either order, but I'll start on this far end. This one goes to ground. So on the board, if you remember, and I don't have the ability to, the college is not giving me funding for any of this, so I just bought what I could get my hands on quickly. Oh, look at it. Anyway, if you look on the board, there's 3 places that say GND. You can connect the ground wire to any of them. I normally use this one way over here. Except for I pulled it out. Anyway, so there's one over here that says, in fact, there's 2 right next to each other over here that say GND, so I'm connected to those. This next one, which is the second one over, it says to, I can't read my own dang diagram. D13 PA5. So on the board, it's labeled D13. So I find D13 and I connect it. It's going to be on this side. There's D13. And remember that D13 is sort of the board label for that connection. And then in software, it's PA5, which you'll get used to because we'll do it a bunch. The next one is probably D12, so I'm going to take the next wire over, connect that to D12. The next wire over is D11, I think. And then the last wire, the one way down here at the end, is D7, I think. So D7. So anyway, I have a ground wire, and then D13, 12, 11, and 7. All right, I'm going to do one more thing on the board, and this is to test my circuit. So on the board, on the same side that I plugged in my ground wire over here, there's a port that says 3V3. So I took a long wire and I attached it to that 3V3. That's a 3.3 volt output, and I can use it to test my circuit. All right, so now we're going to USB cable. So now I don't have any software on this board yet. I'm just going to hook up the USB. If anything happens, that's fine. But I am going to hook it up. And you might not be able to see it doing its thing, but all the lights have come on. So it's getting power. Because of the software on my board, one of my lights is actually lit. That's fine. But what I want to do with that extra wire that I connected to 3.3 volts, I'm just going to take it, I'm going to touch it to the resistors and see on each of the LEDs and see if the light comes on. So if I touch it, if that works, that means that my circuit's wired okay. So that first one tests okay. The second one tests okay. The third one tests okay. And I'm going to assume this last one, since it's on, is wired up okay. And then I'm just going to leave that wire to the side. It doesn't really do anything. All right, questions about that stuff? Okay, I'm going to hide that so we can look at the lab now. Actually, don't let me forget to ask about this. But I have this document so I can take notes for myself about what we discussed and what we decided to do. Okay, so I have lab 7 code here. And I may have to switch back and forth with another file to help, but what the labs usually do is, remember, they have numbered items. And what you're supposed to do is find the number items and then write a piece of assembly code right next to them. So there's one here. Here's the second one. And then here's a third one and a fourth one. So I need to write 4 assembly instructions for this. And I'm trying to be sort of optimal here, so apologies if I'm not letting you have any fun by trying to figure it out for yourself. But morning, Kevin. If you want to work these problems out for yourself, then eventually in the semester you'll probably have the courage to work ahead of us a little bit, or sort of delay watching the class broadcast until you've had a crack at it. Okay. So one thing to remember, and I'm just going to tell you these things, so have a little bit of review here. The OR instruction is for setting bits. The BIC instruction is for clearing bits, and the EOR, or exclusive OR, is for toggling bits. Probably everyone remembers that, but if you don't, probably you just now did, because we've reviewed those a whole bunch of times. So those are the instructions that this lab is practicing with a little bit. How do I actually sort of manipulate the settings on the board to make my circuit function like I want it to? The other thing to note here is that these instructions only affect the targeted bits. So if you don't target a bit, the bit remains unchanged by these instructions, which is nice to have that, because then you can just say, oh yeah, I just want to touch that one bit and clear it, and I don't want to affect any other bits. So that's how we tend to set these up. Okay, so we're looking to use these instructions to solve this lab. So this first one, enable the GPIO-A clock, and I am going a little bit faster. But I'll review for you how these instructions sort of flow. So this load instruction, it gets the address of the clock register. You'll get used to these, but these are memory banks on the board, on the Nucleo board. So we're getting the address of that particular piece of memory. And the reason why we need to access that particular piece of memory is because it's how we control the system clock in terms of connecting to our circuit. So we need to get to this memory bank so we can tell it that we actually need GPIO-A to function in this circuit. So we get that memory bank's address in R3. Then we use a second load instruction to dereference the address and load the current value for that memory bank into R2. So now R2 has a copy of the value from that address, which is the value of this memory bank on the Nucleo board. And then what it's telling me is it wants me to alter this value. So alter R2 so that ultimately we have told this memory bank that we need to enable the A clock. Now I could go into the documentation, but I'm not in the interest of speed. So I happen to know that the A clock bit is the 0th bit. So in other words, I need R2 to be let's see, 1, 2, 3, 4, 5, 6, 7, 8. So this is the 32 bits of R2. And all I care about is this bit right here. That's the 0 bit, 2 to the 0. The next one over would be 2 to the first, 2 squared, 2 cubed, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh, and so on. I didn't actually write down all 32, did I? Or did I? Yeah, I did. That's 8 to the fourth. So this would be 2 to the 31st up here. Anyway, because these instructions only affect the targeted bit, I can just target the one bit I need, which is this bit right here. So I need to enable that bit. Now, whenever you touch a bit, you kind of have to, you're committed to making a value for the whole nibble. So I'm going to make a value for that whole nibble. I only care about that 0 bit. That's the GPIO-A clock, which is in the documentation, but you'll just learn, you'll memorize that eventually. I don't care about these bits, so if I put zeros, I'm just ignoring them. And then all of these I don't care about. So it turns out that in ARM assembly, sort of going from left to right, as soon as you get to a new nibble you don't care about, you don't have to code for it. So what that really becomes then is that. So that 1 is the hex for this nibble. Now I could have said I'm not going to touch any of those other bits, but as long as they're zeros, I can just leave them off my code and it's a lot easier to read. So I'm literally just a hex value that literally touches that 1 bit right there. All right, so that's the hex value that I need to do the manipulation. The instruction that I need is an OR because I need to enable that bit. So the value that I'm trying to manipulate is an R2. So I'm going to OR it with that hex value 1. So this instruction that I've written is the same thing as saying R2 equals R2 ORed with 1. I could write it explicitly, so I could say R2 is R2 ORed with 1. But if I leave that second R2 off, then ARM assumes I mean take the current value of R2, OR it with that, and then store it back. It's like plus equals in C++. Then this last instruction takes my now manipulated R2 value and stores it back into that original memory bank location by dereferencing the address. I'm going to save that and I'm going to keep going. Okay, anybody have questions about that? So the thing to remember from this lab is that this clock register here, to turn on the clock for GPIO-A is the 0 bit. And we'll use GPIO-B and C later in the semester, but for now we just need A, so we just enable that 1 bit. Okay, so now I'm going to go to number 2. So let's see. Okay, so now we're working on the mode register. So the sequence of events is you turn on the clock, you configure the mode, and then you do outputs. So again, I'm not going to go back through this because we've been over it before, but I mean, I do have to a little bit to explain what I'm doing. So the mode register is the hard one to remember. because it's slightly different from all the others in the sense that to set the mode for one pin, you have to set a 2-bit value. So what I need, so let me do 32 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 2, 3, 24, 25, 26, 27, 28, 29, 30, 31, 32. So the mode register is a 32-bit register. And I need to tick, oh wait, it's not those specifically. We'll get the mappings. Okay. I need to enable, I need to configure the pins that connect to these ports on the hardware. I happen to remember them right now, so that's GPIO A5, I think. GPIO A6, GPIO A7, and GPIO A8. So what's labeled as D13 on the board is GPIO bank pin 5 in software. What's labeled as D12 on the board is GPIO pin 6 in software. D11 on the board is pin A7, and then D7 on the board is GPIO A pin 8 in software. These are usually shortened. So instead of GPIO A, they'll write it as just PA5. So pin A5, pin A6, pin A7, and pin A8. If you see me make a mistake, please chat. Help me fix those mistakes. Okay. The other thing that I know from memory is output mode is that pattern. So to make a pin be for output, its 2-bit setting is 0 and 1. All right, so this is sort of the tricky part, and it is the mode register that people usually struggle with for a while. Okay, so in software, I need pin 5 to be that 2-bit configuration value. So because it's 2 bits at a time, the mode register counts different. So these first 2 bits right here, that's PA0. 2 bits at a time. PA1. So I don't care about those. So PA0 and PA1 I'm just going to ignore. This is PA2 and PA3. I also don't care about those. So I'm just going to ignore them with zeros. PA0, PA1, PA2, PA3, PA4 I don't care about. But PA5 I do care about because I need to change the configuration. And I want PA5 to be configuration 0, 1. PA6 I also care about because I need it to be 0, 1. Because I need it to be output. PA7 I care about. So I want it to be 0, 1 so I can do output on it. And then PA8 0, 1. PA9 I don't care about, so I'm just going to zero those out. And then anything above that I don't touch, I can just leave alone. So now I have to translate each of these nibbles into hex. So this first one, that's just 1 in hex. This second one is 2 to the 0 plus 2 squared. That's 1 plus 4 is 5. This third one is just 2 squared, so that's 4. And then I have 2 nibbles that are zeros. So that's my hex value to target the bits in question. Okay, so I'm enabling bits, so I'm going to use OR. I did the same sequence as before with the mode register, so I loaded its address into R3. I dereferenced the address to get its value temporarily into R2. Now I'm going to alter the value in R2, which is by ORing it with that value I just worked out. And then I'm going to store the manipulated value back into memory at R3, which presently is the mode register. And I'm going to save that. This will take me longer than I thought. Sorry for those of you who have seen it before. But maybe it's helping sort of get you warmed up again. Okay, anybody have questions about how I did those things? So the clock register is 1 bit per setting. The mode register is 2 bits per setting, which is what makes it a little bit more confusing than the rest. So number 3 is the output register, and that's back to 1 bit per setting. So the same sequence here. We load the address, and this output is how we actually turn the lights on and off. The mode sets it so that we can turn them on and off. The output allows us to actually turn them on and off. So we get the address of the output register into R3. We dereference to get the current value, and now we're going to write code to manipulate it. So here it says set the bits, which is another way of saying enable. Set the bits with D13 and D11. Okay, so for this one, I need, remember 1 bit per, so I'm really just going to do, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 17, 18, 19, 20, 2, 3, 4, 5, 6, 7, 28, 29, 30, 31, 32. D13, if you remember in software, is pin A5. D11 is pin A7. So it's kind of skipping over one in between them. So let's see. So remember now, at this point, it's 1 bit per output, which is confusing because when we do mode, that's 2 bits. Now we're back to 1 bit. So this bit right here, that's PA0, and I don't care about PA0. I don't care about PA1, I don't care about PA2, I don't care about PA3, I don't care about PA4. I do care about PA5. I don't care about PA6, but I do care about PA7. And then, since I'm not touching any nibbles above that, I can just ignore them. So that's my value to, that's my nibbles to manipulate the bits in question. This one's tricky because that's 2 cubed, which is 8, plus 2 squared, which is 2. So that's 10, which in hex is A, followed by this 0. Followed by a 0. So to do this number 3, I need to do an OR with those values. So I'm going to OR. R2 again has the value being manipulated. So I'm going to OR it with that. And save. All right, and then this is number 4. Oh, there's a number 5. I didn't see that. There's a number 4, which is clear the bits. So now I need to do a bit clear, a BIC, with D12 and D7. So I need, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 24, 25, 26, 27, 28, 29, 30, 31, 32. D12 is PA6 in software. D7 is PA8 in software. 8 in software. So I need to do a bit clear on R2 with some value. Let's see. So I need 6 and 8. So I don't care about 0. I don't care about PA1 or PA2 or PA3 or PA4 or PA5. I do care about PA6. I don't care about PA7. And I do care about PA8. And if I touch a nibble, then I have to sort of finish the nibble, even though I'm not touching these, so I just zero them. And then I'm not touching any of the nibbles above there, so I'm just going to ignore that. So in hex, that would be, this first nibble is 1. This second nibble is a 2 squared, so that's 4. And there's a 0 here. So that's my bit clearing value to make sure that. So what's going to happen is the lights connected to PA5 and 7 should be on to start. The lights connected to 6 and 8 should be off, but then I'm going to immediately toggle them so they'll sort of take turns being on and off. Okay, so ready for number 5. And it's not as fast as I was hoping, but hopefully this is helping some of you, and you can review it as well. Okay, so I'm just going one numbered item to the next. So inverting bits is exclusive OR, so I'm going to exclusive OR R2 with something. So I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 6, 7, 28, 30, 31, 32. Every time it says ODR, remember it's 1 bit per pin. If it says mode, it's 2 bits per pin. But down here on number 5, it says ODR, so 1 bit per pin. So D13 on the board is PA5, D12, PA6, D11, PA7, and D7 is PA8 on the board. Okay, so to get the value, I don't care about 0, 1 bit here, ODR. I don't care about 1, I don't care about 2, I don't care about 3, I don't care about 4. I do care about 5. I do care about 6, I do care about 7, I do care about 8. I touched this nibble, so I need to sort of finish by zeroing out the bits I don't care about. And then I don't care about anything above that, so I just ignore it. The hex for that, that nibble becomes 1 in hex. This one becomes 1 in hex. This one is 14, so 8 plus 4 plus 2 is 14, which in hex is an E, and then this last one is a 0. So that is my toggling value. And now you're going to have to be patient with me because I'm going to have to go through the compiling process. Before I do that, though, does anyone have any questions for me? I'm going to do this relatively quick, and then I'm going to take a short break so I can get myself a glass of water so I can keep my voice going. Yes, so homework 7, right after I show you what the circuit's supposed to do. So I'm going to do that real quick. I'm going to go through the compiling process real quick, show you what the circuit is supposed to do, and then take like a minute to run into the kitchen and get a glass of water, and then resume with homework 7, yes. Okay, so hopefully, and again, this will be posted on YouTube, so if it went a little too fast, you can get it. you can review the video. So let me make some adjustments here. And I need the vertical camera. So you can see it. So I'm going to go do the compiling process. So I'm going to compile it. I'm going to create the ELF file. I'm going to fire up OpenOCD, and then I'm going to use GDB to burn the software and launch the program. Hopefully. We will find out. So I just compiled it. Now I'm going to produce the ELF file. Now I'm going to launch OpenOCD. I'm actually going to do that in my other terminal. So I have two terminals running. Which hopefully you're seeing that. Okay. Now I'm going to go back to the first terminal. I'm going to do all the GDB stuff to get in there and run it. Right, yeah. Hopefully that showed that I connected. Target needs reset. I think I'm okay. Load. And then monitor, reset, halt. Now at this point in the earlier labs, we've been doing stepping so we can control the flow of execution. But for this lab, it's okay to just do a continue, which will just sort of let the circuit start running. You can shorten continue to just a C, by the way. And if everything goes as expected, you should see the lights toggling on and off like they are on mine. Okay, so that's step one. Thanks for your patience. It's the first time, but we should, in theory, each time we do a wiring setup, we should be able to go just a little bit faster. That's what the circuit should do. So the pairs. So that's the D11, D13, and then D12, D7 taking turns. That's what the E-OR toggle is doing, is toggling current, no current, current, no current constantly to make them flash like that. Okay. I hope I don't lose anybody. What is next is homework 7. So, and I don't know how patient you'll be, but if you're willing to wait me out, we can all take a short break. I'm gonna go get some water. Maybe you can do the same. Just a minute or two, and then I'll go over homework 7. And when I come back, if you're needing to get up and leave because you got something else to do, if you could just give me a few more moments to return and remind you how we're going to submit our work before you do that, and then you can watch the video later. But if you're willing to stick it out with me, then let's try to keep going and make up for the day that we lost on Tuesday. All right, so I'm going to take a short break, get myself a glass of water, and then we'll do homework 7. All right, hopefully I didn't go too fast to that someone's in the bathroom right now. But what I'll do by chat, just to give those people a couple seconds to get back in their seats if they stepped away. Is anyone interested in doing a Slack or Discord for the class, that which would be a way for me to answer questions, but probably more importantly, a way for you guys to step in and help each other, which we're going to need sort of maximum amount of collaboration, I think, to get over the fact that we never get to be in the same space and actually work together on anything. So is it, just in chat, is anyone, just say yes or okay or something if anyone would be interested in. So Discord, do you guys want me to set up the Discord, or do you want to sort of set it up and own it, and then I can sort of facilitate invites? It's totally up to you. Yeah, Discord is cool that way. So I guess so. The main thing I don't want to do is discourage discussion, and I can take a lump or two. So if you want to use Discord to complain about the work that I'm doing, don't be shy about it. I won't hold it against you. But that said, the reason why sometimes I'm hesitant to create it for you is because I don't want you to feel like someone's monitoring it and you don't have the freedom to speak amongst yourselves. But I'm guessing that it might be easiest if I set it up and then send out invites to everybody. So that's my plan, unless someone in chat wants to sort of take ownership of that and sort of you guys just own it amongst yourselves. Okay, so you can email me if you have any different thoughts, but what I'll do, I have to basically broadcast all day today, so it won't be till tonight or tomorrow morning probably, but I'll set up a Discord for this class and get invites out to everyone so we can start using that channel. So I have updated all the labs so that they all have that diagram that you were looking at this morning, and I hope that helps. And now that you see me sort of go through a wiring setup, hopefully that helps. Sorry, I got to turn this flashy thing is starting to be distracting to me, so I'm going to hide it and power it down. Okay, so I'll try not to make this last too long. So we'll do homework 7. Labs 8 and 9 go together nicely, so we can kind of just do both of those next week. So don't worry about lab 8 unless you want to go have a crack at it. We'll do lab 8 and 9 next week. So I'm not going to be too much. I'm not going to be hard on anybody for when you get your work in, but the plan is that you try to get the week's work in by the end of the week each week. So for example, this week, if you could get lab 7 and homework 7, lab 8 is sort of, we have to put that off. But if you get lab 7 and homework 7 emailed to me so that I can sort of work through them over the weekend, that's ideal. If it doesn't happen, then as soon as you can get it finished, send it to me and I'll process it when I receive it. In terms of the labs, what you'll send is only the code that you touch. So you don't need to send the .ld file or the .cfg file. All you have to send is the .s file for the code that you touch on the labs. And for homeworks, you'll just send the PDFs as normal. Although what should be true is that you get 100% on the rest of the homeworks because we're just going to talk through them together every week. normally on Tuesday, but because we lost Tuesday this week, we'll do it today. Okay, so let me move the browser over. And then hide some things. Okay, ready for homework 7, I hope. There's nothing down here to look at. That's kind of depressing. Oh well. Oh, I know what I can put there. I know what I can put there. I can write notes over here and add them. Okay, so homework 7. So the new thing this week is called 2's complement. All we mean by that is a way to store negative integers in binary. That's all we mean by 2's complement. Is a way to store negative integers in binary. I'll give you my textbooky answer. I'll show you on the screen. My textbooky answer looks like this. So what is 2's complement? It's too big. It's the most common way that we represent signed integers on computers. And by on computers, I mean in binary. So 2's complement is the most common system for representing signed integers, negative integers in binary. Can you still see everything? Oh, it hasn't caught up yet, has it? It'll get there, I think. Well, I pasted in a fancy answer in there. There it goes. Anyway, so 2's complement is the most common method for storing signed integers or potentially negative values on computers or in binary. Its advantage is that you can use the same math operations on signed integers as on any other binary number. So the neat thing about 2's complement is that the circuitry to do arithmetic on 2's complement is the same as it is for any other binary arithmetic. It's a pretty neat system. I'll show you if we get a chance kind of how it works. All right, so that's what we're talking about. How do you actually make negative numbers? You do it in binary with this system called 2's complement. The second question is kind of a trick question because on ARM processors, how are all integers represented? In 2's complement. So the reason to know this when you're working in ARM is because that's the way that ARM represents all integers. So it turns out in ARM that all integers are signed, meaning all integers are always either positive or negative. So ARM doesn't deal in unsigned integers only. The next one I'm going to give you the answer, and then on the notes page I'm going to show you how that works. In fact, let's stop and let me put some notes in about signed integers. So we're going to start with 8-bit integers. So let's just say we have this value in binary. I'll put a 0b in front of it just to remind you. I put a space because I think it was hard to read there. So that's a 0, obviously. That's 1. You know these values. 2, and so on. So in signed integers, 0 is kind of special. In the signed system, they actually reserve this bit at the top. The high bit is the sign bit. So what I mean by that is this bit right here. In 2's complement, that bit is not part of the value. It tells you whether or not the number is negative. So if it's a 0, it's a net positive number. If it's a 1, it's a negative number. So let me do, for example, this number right here. I know it's negative because the high bit, the sign bit, is 1. So I don't necessarily know what the value part is just yet, but I do know that the number has to be negative because this bit, which is reserved to mark it as positive or negative, is a 1. I know this is a positive number because the high bit is a 0. And I know this one is a positive number because the high bit is a 0. All right, so here's the funky thing about it. We don't know what this value is. This value is simply decimal 1. Probably if I just say 1, you know what I mean. This value is just decimal 2. All right, now the funky stuff. So if you see a 2's complement value, which they all are in ARM, and the high bit is a 1, you already know that this value is negative something. That's what that bit means. Hopefully everyone's okay with that. Let me see if we still got most of our people here. We do. Okay, so I already know that this value right here is negative because this high bit is 1. And that's what it means in 2's complement, that what you're about to see is a negative number. Now I happen to know, I think I'm right about this, that value is actually negative 1, which is super, super funky when you first encounter it. But I know it's negative, and this value is negative 1. So I'm going to show you how I got that, how 2's complement works as a means of answering number 3. All right, so number 2 is all integers on ARM are represented in 2's complement. Okay, so number 3. How do you find the 2's complement of a number? So the 2's complement, the reason why we say it's a complement is because you can go back and forth between the positive and the negative number by complementing it. So for example, to go from, let me separate this part out so you can see where I'm working. So if I want to go from 1 to negative 1, it's 2's complement. The way you do that is, see if you can figure it out. So the first thing you do is you take what's called the 1's complement, but all I did is I inverted all the bits. So if I want to get the 2's complement of 1, the first step I do is I invert all the bits, which we call taking the 1's complement of the value. So I invert all the bits, and then as a second step, I add 1. So to get the 2's complement of positive 1, I invert the bits. So notice the zeros became a 1 and the 1 became a 0. That's called the 1's complement. Then I add 1 to that, and I get the 2's complement. Now we haven't talked about binary math, which we're about to do, even though you don't really need to know how to do it very much. So the answer to that question is the convenient way of getting the 2's complement of a number is to invert the bits and add 1. So now I'm going to go the other direction. So now I'm going to do the same problem, but in reverse. And then we'll do a little bit of binary math while we're at it. So now let's start with -1. And go to +1. All right, so to do that, we take the 1's complement of -1, which is invert all the bits. We add 1. And that gives us the opposite sign. So the 2's complement means you take the positive and you get its negative, or you take the negative and you get its positive. Hopefully everyone saw how that worked. It's kind of neat. All right, so we'll hold off for a second on doing binary arithmetic more formally until we have to. So let's keep working through the questions and see what comes next. What is the 8-bit binary and hexadecimal representation of the decimal number 5? Well, that's pretty easy. So it wants it in 8 bits. So remember here that we need to be thinking 2's complement, because that's what this assignment is really about. So the binary is going to start with the 0. That's because it's a +5. And then we just render a 5. So 5 is, let's see, 0, 1, 2. That's 5, right? So that's the binary of 2's complement, +5. The hex is simply 0x5. Oh, well, technically, if it's 8 bits, it's 2 nibbles, so 0x05. So you still take the sign bit and make it part of the hex value. So that nibble with the sign bit in it is 0. And this nibble is 5. So that's number 4. Check in chat just to make sure I'm not leaving anybody behind. Okay, number 5. The 8-bit binary and hexadecimal representation of the decimal number -5. So it's actually harder to just write the negative values from scratch. So the easy way to do that is to start with the positive one and get yourself the negative one. So one of the reasons why I asked you the question that way is to make it easier to do the next problem. So I'm going to start with that. I'm going to just let me check and make sure I'm not too far. I'm a little far up the screen. Let me hit enter a few times. All right, so there's 5. And I need to get negative 5. So I remember that to do that, I invert all the bits. And then I add 1. Which gives me 1, 2, 3, 4, 1, 0, 1, 1. And I just have to trust that the process actually gave me the negative value. But this should be negative 5. And then to get the hex of that, I just do the old familiar hex process, which is convert the nibbles. So that's 15, the upper nibble, which is simply F. This is, what is it? 0, 1, 2, 8, and 2. That's 11. So that's C, A10, oh, B. All right, where else does this assignment, this homework go? Okay, so I'll give you the textbook answer and then I'll show you how it works. Sign extension. So sign extension is how you make a 2's complement value bigger while preserving the fact that it's positive or negative. And I'll show you a couple of examples. So that's all sign extension is adding bits to a 2's complement value while preserving the fact that it's positive or negative, preserving its sign. So sign extension. So let's say, for example, we have that 5. If we wanted it as 16 bits, if we want this 8-bit value now to be 16 bits worth of memory, what you do is you take the sign bit and you extend it all the way up through the extra bits that you need. So here's my sign bit from the 8-bit value. It's a 0. And if I want a 16-bit value that's still positive 5, I take the sign bit and I simply extend it all the way up. I'll do the same thing with the negative 5. All right, so what we want now not a plus, an underscore, please. All right, so sign extension, you take the sign bit and you extend it all the way up as far as you need it to grow. So if I need 16 bits, I'm going to take that 1 and I'm just going to extend it all the way up. So what that does is it allows a larger value to be extended out as a more or less a copy without losing the meaning of a smaller value. So that's still -5, but consuming 16 bits. That's what sign extension does. This is still +5, but consuming 16 bits. I just did 7 and 8. Oh, and hex. Well, hex is easy because it's just 0 nibble, 0, 0, 1. And then I just sign extended -5. And then I just use the old all ones is an F. All ones is an F. All ones is an F. And then this one was A. So the funky thing about this is that 0xFFA in ARM is -5. Which is pretty crazy. All right, we're just about there. Thanks for bearing with me. Which one did I write wrong? For -5. For +5, you're exactly right. It's 0x001. So you're correct. For -5, that's question number 8. All these nibbles, because of the sign extension, become Fs. Yes. Yes. You're right. I did +5 wrong. Where did I copy it from? Some dumb place. You are correct. So thank you. We did this one wrong. Number 7, which should have made this 5. You're correct. Thank you for the fix. And then I'll show you the answer to the 9th one and then where to find the answers for the rest of them. I'm just hitting pause for a second. Okay, so there's a couple of ways that you can do number 9. Placing the new value into register R1. Okay, so the point of number 9 is to draw your attention to the fact that you can actually perform this process of inverting the sign. So you can, in code, make a positive be a negative or a negative be a positive with instructions. So what number 9 is asking me to do is convert the unsigned value in R2 to its 2's complement. So one thing you can do is you can toggle R2. And you can do it this way. This isn't totally correct, but basically you can target every bit with a toggle in R2. Then you can add 1 to R2. Remember, this is sort of invert the bits, add 1, and then Between registers, you can just do a move. So now I can move as copy. I can copy R2 into R1. So that's one way you can do this problem. Is it B? What did I write? Did I write A? You're correct. Thank you. Number 8 is B. Good catch. Yeah, because that's 11, not 10. Good catch. Okay, sorry, I had to jump back for that. So this is the assembly way of applying that. So all we're doing here is at the end is basically R1 is the opposite sign of R2. So if R2 had a positive value, R1 has that value as negative. If R2 had a negative value, R1 has the positive. There is another way to do this. There's an instruction in ARM called move and negate. Which will copy the value of R2 into R1 and at the same time negate or invert all the bits. You still have to do the add 1, but this is an alternative. So ARM actually has an instruction that allows you to copy the value, flip all the bits over, and then we can add 1 to R1 to complete the process. And then the last one I'll leave for your one little bit of, so that we can finish the broadcast. The last one I'll start you and then sort of leave you to finish, because it's not really a thinking one. Okay, so the main difference between the sizes, like an 8-bit signed integer and a 16-bit signed integer, is that you can store more and bigger values as you get more bits, which I think intuitively makes sense. So I'll show you where to find this, and then you can go sort of finish the answers, and I'll do one of them. So anyway, if you go to if you type a Google search for integer computer science, you get a Wikipedia page for integer computer science. And if you scroll down this screen, there's a table. There's a table here that tells you the ranges of common types. So the first column is the number of bits. So if you go to 8 bits, you'll see that it'll say signed 8 bits can represent a range and unsigned 8 bits can represent a range. So signed 8 bits can represent all values from 0 to 255. So unsigned 8 bits goes from 0 to 255. Signed 8 bits goes from negative 128 to 127. If you want to at some point, I want to let you get away from me here. We can talk about how this works. It'll come up. Now remember that in ARM, everything is signed. So asking you about the unsigned one is in part really just about teaching computer science, to understand that if you have more bits, you get a larger range of values. But in ARM, everything is signed. So this is the range of 8-bit integers in ARM. All right, that gets me to where I intend to stop. Does everyone, hopefully everyone is confident that you can use that Wikipedia page to get the answers for 16-bit signed and unsigned and the answers for 32-bit signed and unsigned. The 32-bit ones get quite large, so those are miserable to type. Sorry about that. But that's meant to drive home the point that you sort of understand how integers work a little bit. Okay, so I am going to shut up. I'll wait for a minute or two to see if we've got any questions. And then I'll sign off here in a bit. If you're in P&A 2, apologies. You're not going to get as much of a break as I would like both of us to have. So remember, so for this week, I'll add it to the notes. So lecture notes, review, do this week. Lab 7, which is the main.s for Lab 7, and homework 7, the PDF file. We'll do Lab 8 and Lab 9 next week. So Lab 7, the main.s, when you have it working, and what I'll do is I'll get it and run it on my circuit and make sure that it works, and then we'll help you fix it if it's broke. And then the PDF file for homework 7, make sure you finish that last question using the Wikipedia page. And thank you, everybody, for watching out for mistakes and helping me fix them. No, I'm not taking roll, so I hope everyone uses what they can of the broadcast or watches the video or both. But no, I won't take roll. I'll just get the points off the submissions of assignments. Because some people may be working or doing other things because of the disruption. So I'm trying to be I'm trying to be flexible to the max. Okay. Last chance. I will be, well, for you guys, I'll see you next Tuesday at 8:30. Normally on Wednesdays, I'll be on at 10 just to answer random questions. And you can always email if you have a question, so I can help you get things working right. So best if you can submit this week's work sometime like around the close of business on Friday so that I can work through and get your scores down over the weekend. All right, thank you. Thank you for being here. And if you're in P&A 2, I will see you in about 45 minutes, I think.